I'm in the wrong camera. That's okay. And you can't see that very well. That's a bummer. I'll figure that out. You can't see the board very well from the camera. I'll figure that out sometime later. Okay, so I have this tensor. It's got 3 elements. I've got this vector and this other vector. They both have 3 elements. This one has 27 elements. We're going to sum over j and k. So how do we think about this? So I'm going to come down here and do it. So let's think about varying the first index. So the first index can be 0, 1, or 2. So let's think about epsilon 0. Then j and k are going to vary 0, 1, and 2. I know that if I'm picking the first element here, the first one is 0, then I can ignore 0 for the other 2. I only need to worry about 1 and 2 here, and 1 and 2 here. So, let's keep that. Epsilon j, k, bj goes with the second index, bk goes with the third index. So we're going to loop over every possible option for j and k. So j can be 0, 1, and 2. So think about this like a circle. I, j, k, or 0, 1, 2. And if I go in the circle in this direction, I get a 1. And if I go in the other direction, I get a -1. So I need to write down the cross product. So epsilon is 0. So j, if j is 1, b 1. Oh man, there's a robot somewhere that's trying to get my attention. So v is 1. What's the option for k? If I is 0, j is 1. What is k? 2. 2. I could do this x, y, and z, but I'm going to do it 0, 1, and 2. Okay, so that's one element, and then the other element is when these two are reversed. So this can be 1 and 2, or this can be 2 and 1, and I pick up a minus sign. So we'll call this y. Y is the cross product of v and b. F. That makes more sense. F is the cross product of v and b, because it is. So F0 is equal to this. So F0 is V1, V2 minus V2, V1. Does that make sense? Does that look like a cross product term that you've seen before? So we do it with this totally antisymmetric tensor. And I like drawing them in a circle like this, because that helps me keep track of what goes in what order. So then F1, let's do this one much faster. Epsilon 1, j, k, v, j, v, k equals what? V 0, v 2 minus v 2. Oops. 2, sorry. That's backwards. So we're looking at v1. The next cyclic one is 2 and then 0. So v2, v0, and then we get a minus sign with 0, 2. Does that make sense? There'll be a homework on this so that you can play around with it a little bit later. Okay, stop me. Where did I put the eraser? Stop me. I'm going to now never speak of this again and just use it. So if you want to see any of that stuff again, stop me and holler. Next math thing, the gradient. Nabla. What do you guys call this thing? Do you know what it is? What does it do?
It's the gradient.
Was that?
The gradient.
It's the gradient. So what is it?
The derivative. Each component of the derivative.
Each component of the derivative. So it's I hat d by dx. Also, again, because I'm lazy, dx is d by dx. I just shorten the notation. I'm not the only person that does this. This is in lots. So this is I hat d by dx plus j hat dy plus k hat dz. So here's our gradient operator, and it's a vector. But it's a vector of verbs, so it's a vector that does stuff. So we can do stuff with it. One of the things we can do is dot it into a vector. Does anybody remember what this is called? Something holler. It's the divergence of the vector. And it's equal to the dot product of the nabla and the vector, and it's dx vx plus dy vy plus dz vz, and it is a scalar, even though we have these vector components. This is a thing that doesn't have any components anymore. You can see that it doesn't have any components anymore by writing it in Einstein notation. Write this as di vi. I have two indices and they're repeated, so I have no more indices. So this is a scalar. It's not a vector anymore. There's no more components. We've consumed all the components. You can also take a cross product, del cross v. What is this? Epsilon ijk. It's the curl. dj vk. And I'm not going to write it all out because I just kind of did. Here's the curl of the vector. Here's another vector operation that you may not have seen before. I could take another vector, v, and dot it into the gradient on the left-hand side. What does that mean? That means vx dx plus vy d by dy plus vz d by dz. It's a scalar, even though it has all these components in it. And it's still a verb. This is still something that does something. What does this represent? We'll talk about this operator a lot coming up. This represents pushing stuff around. That'll become obvious in a minute. Okay. The fundamental theorem of calculus, so vectors, nabla. If you ever get confused on what nabla is and how it behaves, feel free to stop me and ask me. Okay, the fundamental theorem of calculus. Who can tell me what the fundamental theorem of calculus is? It's fundamental, guys. You guys have heard of it, right? You remember what it says? Can't quite remember. It's one of my very favorite things. And it's very simple. And it's really dumb. You're like, that's it. The integral of df equals f. That's it. If I integrate a derivative, I get a thing back. Right? So, or a better way to think about this is the integral from a to b. This is the pure way to think about it. This is how I learned it. But if I go from a to b, then of df, then I get f evaluated at b and a. I get an f evaluated at the endpoints. So if I integrate a derivative, I get the quantity at the endpoints. Super fascinating and really valuable physical process. The reason that I'm bringing this up right after these vectors, this is not an incongruous jump. This is because if I take the integral of the divergence of something, what do I get? Over some volume. So I've got some volume v. In space, I've got some vector quantity. I'm taking the integral, the volume integral of the divergence of that quantity. What do I get? Well, I'm integrating a derivative, right? So I'm just going to get the quantity evaluated at the ends. So, but the ends here, the ends are just 2 points. Here, the ends are this whole surface. So it gets simpler, but I still have an integral. So the integral of the divergence of a thing is the quantity on the surface. Is that familiar to everybody? Right. Whose theorem is that? Do you remember?
Divergence theorem.
That's a good way to call it. People will call it Gauss's theorem. divergence theorem works just fine. Okay. Similarly, if I have a curl of V, and I integrate this, you guys have all seen this before, so feel free to jump in and tell me what I'm going to do. I'm going to integrate this over an area, d squared x. So if I have an area and I have some vector field in it, and I take the curl of that and I integrate it over the surface, this is the integral over the curve of the field on the bounding curve. That make sense? So fundamental theorem of calculus gives us Gauss's rule, gives us Stokes' rule. I'm not going to call them Stokes or Gauss's anymore. I'm just going to use it. Okay. A couple more math stunts that you're going to need to know about. That you already know about, but I'm going to say out loud just so that I've covered everything and given you an opportunity to say, I don't remember how to do that. Yeah. The last thing I want to talk about, I'm going to skip talking about some of those because I think we're all set. Oh, that's out of order. Last thing I'm going to do, because I'm going to do it, so if I have polar coordinates, so I'm in cylindrical coordinates, and my coordinates are r and theta. If you want to take the divergence of a coordinate of a vector in this coordinate system, then you need to do it right, and you need to remember that the unit vectors move in space. So my unit vectors here are r hat and theta hat. If I want to talk about nabla, which is I hat dx plus j hat dy plus k hat dz. If I want to, actually let's do this just in 2 dimensions. In cylindrical coordinates, the z just kind of shows up for free. So let's just do it in 2 coordinates. So nabla is I hat dx plus j hat dy. If I want to do this in cylindrical coordinates, then we need to do 2 things. So we need to first replace the variables. Just substitute. And then second, we need to don't mess up the chain rule. So don't mess up the chain rule when you're doing it. So nabla in cylindrical coordinates is r hat d by dr plus theta hat 1 over r d by d theta. Has everybody seen something like that before? If not, I can do it again slower. How do I get here? Where does this 1 over r come from? How do you get the 1 over r? Okay, if you want to go from here to here, you got to convert these unit vectors, and you got to do the chain rule. So you say dr, dx equals dr dx dr plus d theta dx d theta. Make sense? And dr dx, you can sort out what that is. So how do we sort that out? So r equals x squared plus y squared. We'll ignore z for now. And theta equals the inverse tan of y over x. These are the coordinate transforms you can just look up. So dr dx is what? Well, I got to do this I got to do this derivative. So I'll just tell you what it is. It's x over x squared plus y squared. And then d theta dx, well, I got to do some calculus there, and I don't really care. I'm not going to do the whole derivation, but you do this derivative, simplify, and you get, where to put it? Oh, sorry, this turns into cosine of theta. You look at that, this turns into cosine of theta, and this turns into 1 over r sine of theta, d theta, dr. So if I'm going to convert from from Cartesian coordinates to cylindrical coordinates, the first thing to do is change all the derivatives using chain rule. The second thing you need to do is change all the unit vectors using geometry. So I hat is, x hat is cos theta r hat minus sine theta theta hat, and then y hat equals, I'm going to skip some of the algebra because watching me do algebra isn't very interesting. So we do that, and we plug those into here, and then you just do a little bit of algebra. There's like a page of algebra that's kind of tedious, and then you're left with this final equation. Did everybody follow all of those bits? Okay, I kind of went fast because this is all, in my head, this is all review, but I want to make sure that I touch on the things and give you guys a space to say, yeah, I don't remember how that worked. I think there's a homework problem on this one. And then, if you want to, let's see. Yeah, I'll leave the rest of it for homework because that's good. That's a good homework problem. Okay. Is that it for math? That is it for my math refresher. It goes by kind of fast. We'll come back to all of those things again as time goes on. And if any of those things, like later you're like, yeah, I don't remember how that thing worked. Are you still recording? Come talk to me. Okay. Now we'll start the new stuff that doesn't feel like review. So now I really need you to stop me if I say something confusing, because I have a tendency of talking faster and faster and faster and faster, and I can cover an enormous amount of material very quickly. You guys don't stop me and make sure that you understand what I'm saying. Okay, so what are the major equations that we're going to deal with this semester? So the major things that we're going to do this semester, my big takeaway is if you can derive Navier-Stokes cold from scratch, I will be happy. So Navier-Stokes says this: the time derivative of velocity, I'll write it like vectors, plus v dot grad v. Okay, this is kind of a confusing little object because it's kind of complicated, because the parentheses go here, and I have this vector operator that I'm operating on this vector. I'll talk about this in a minute, but this is dv dt. I'll show you why in a minute. Equals minus 1 over rho, there's the density, grad p, that's the pressure, plus nu del squared v. Okay, this is Navier-Stokes. I'm going to derive it for you. I'm going to derive part of it for you right now, derive the other part of it next week. This is Navier-Stokes. Now if I cut this part off, I get Euler. So Euler's equation is Navier-Stokes' equation with the viscosity term taken off. That'll make more sense later. I'm only going to talk about Euler today, so we're going to ignore this term, this last term. I'll derive it on Monday. The other equation that I think is important is the continuity equation. There are several equations that you'll deal with, but these two we're going to use all the time. So this one is about density. d rho dt plus div rho times v equals 0. This is called the continuity. So this one talks about how velocity changes with time. This is the force law. This is F equals ma, written in a slightly funny way. And this one is mass conservation. So this tells me that mass is conserved. I'll show you why you see that from here in a minute. But I wanted to write these down big because we're going to talk about them a lot. God, I hate these boards so much. They're so awful. I want all this space, but I know that I can't actually erase that. Maybe I'll just get a poster. Get a poster printed up with obvious space. Let's see. I'm going to try it. Let's see. Maybe I can erase this board. Anyway, okay, I'm going to write it over here for completeness. dv dt plus v dot grad v equals minus 1 over rho grad p plus nu del squared v. This is Navier-Stokes, and continuity is d by dt of rho plus div rho v equals 0. So where do these come from? These are important. I'll show you where they come from. Let's get them. Let's get continuity first because it's easier. I don't actually know if it's easier, but we'll do it first. Okay. I have a fluid. I live in a fluid. Air all around me. I have a bottle of fluid. Say I just have an imaginary surface. We're going to draw a lot of imaginary surfaces in this class. So if that's not something that you've done a buttload in your physics classes already, that's a thing we do. So we will. So I have some fluid. Say the patch of the ocean. Here's a fish. So I have some patch of fluid. In the fluid, there's some mass, m. Yeah.
Is that the fish?
The mass?
Yeah.
No, just the fluid. Not of the fish, just of the fluid. This is equal to the integral of rho v cubed x over my volume. Call this volume v. So mass is the integral of density over space. This is seems kind of dumb, but it's actually a very important equation. So make sure that that makes sense to you. Yeah. So I want to think about the partial derivative of m with respect to t. Now, when you write partial derivative, that means you hold everything other than this quantity fixed. And that matters a lot here because there's many quantities. So what are the quantities that we have that can change? We have x, y, z, vi, and rho. Those things can all change. Really have an internal energy too, unless I have something else. So there's a lot of variables that can change. This is the partial derivative of m with respect to t, holding everything else fixed. Only t. M is the free parameters on m are x, y, z, and t. dm dt is what? What is the change in mass inside of this fluid? How would I sort that out? So let's have a simpler thing. If I have a box full of kittens, what is the change in time of the number of kittens in the box? Don't be dark. They all stay alive. How can the number of kittens change? Well, if they all stay in the box, there's no change. But if some of them leave the box, then what's the change? However many left. All right. So the change in mass is whatever leaves my control surface, right? So it's just the integral over the surface area. So I'm going to integrate this surface. Everywhere on this surface, I'm going to ask who's leaving. So that's going to be the velocity times the density dotted into the surface. If it's rotating like this, it doesn't matter. Velocities, like if all the kittens are just running in a circle in the box, they're not leaving. It's only when they cross, it's only when their velocity is perpendicular to the surface that they leave. So v times rho is the flux. So the amount of mass that leaves is going to be v times rho dotted into the area. And it's going to be minus that because of the way that, really the only way that it makes sense is if the normal is outwards and the velocity is dotted to that. Okay, does this make sense so far? Now I'm going to simplify this. So this is a volume integral, and this is an area integral. How do I turn this volume into an area integral, or the other way around? Which one is easy to turn into the other kind of integral? Using stuff that I erased already. So we can go from an area integral to a volume integral if we introduce a divergence. Remember that? So this is equal to minus the integral of the volume of div rho v d cubed x. And on the other side, this is equal to partial t of the integral of rho d cubed x. Sweet. So what I did, I wrote down mass. I wrote down how I know it's got to change based on the flux. I make everything a volume integral. Now that everything's a volume integral, I can put it all under the same integral. So I shove everything to one side, and I'm left with an integral over v of d partial rho partial t plus, I'm going to move this to the other side, plus div rho v, we integrate all of this, d cubed x, equals 0. Okay. Now, the inside, you'll notice, is over there. So I have this equation, and I integrate it over a random ass plot point in space. And since if I integrate something over something random, and I get 0 all the time, then the thing inside has to be 0, right? So the whole integral is 0, but I can change the volume however I want. So the inside has to all be 0. So d rho dt plus div rho v equals 0. And there is continuity. Everybody follow all that? This is a thing. You will see this on the homework, and you will see it on the midterm. One of the questions is probably going to be derived continuity forming. So make sure that you have your head around that derivation and how it goes. Not because I think it's like particularly hard, just because I think it's important to be able to work through these processes. Okay, let's get Euler now. Oh, what time is class done? 2:35, right? Okay, I guess around 15 minutes. Okay, Euler. So, can I do it in this space? I think I can. Okay. F equals what? You're a physicist. F equals? MA. F equals MA. What's A? A is dv dt. Okay. My handwriting is ass. It's terrible. I do my very best to keep my partial derivatives and my full derivatives different. If it's ever unclear, you should ask, because there's a huge difference and it makes between the two. Here, it's very important that this is a partial derivative. If I use the full derivative, I would have to take the chain rule and get the other components too, like I'm going to do now. dv dt, v depends on x, y, z, and time. So you guys all remember chain rule. Chain rule is on my list of math things that I went up that I should go over, but I didn't go over it because I figured everybody's solid on chain rule. If you're not solid on chain rule, let me know and we'll talk about it. So full derivative of velocity with respect to time also depends on x, y, and z, which also depend on time. So the full derivative is partial v partial t plus partial v partial x partial t plus partial v partial y partial t plus partial v partial z dz dt. And x is a derivative of a vector. V is a vector. It's still a vector quantity. How did I get that? That expanded a lot of things. It's just chain rule, t by itself, and then all of the other things that also depend on t. Yeah.
There's no last part of that.
The same thing but with z. So it's dv, dz, dz, dt. So we got partial v, partial t. That's important thing one. Plus partial v, partial x, partial t. Then there's other terms, but let's just talk about this one for a second. What's dx dt? Somebody say something. In which velocity? Yes? In the x direction. This is vx. So this is vx. This is dv dx. Plus dv dy. Vy. It's dx dy dt. We'll just call it vy now. Let's simplify. Vx plus dvz plus dv dt vz, because dx dt. So this let me color code stuff. So let's stare at this for a second. I really wish it showed up better on here. I am probably going to move the room of the class downstairs into the basement because that room is better. Watch out for an announcement. Those of you who took XGal with me were there already. So here, this is the, oh man. I'm just gonna, I need a garbage over here. Is there a garbage over there? Nice. That was very satisfying. I am not an athletic individual. So when things go in. So V, this V, this V, this V, and this V, this V, this V, and this V are all the original V that I'm taking the velocity of, okay? Ah, yay! This V, and this V come from chain rule. Come from the derivative that we were taking. So that velocity comes from the chain rule as well. I can simplify this. This is a velocity thing. So this is a vectory thing. This is a vectory thing. So this is V dot grad operating on V. Does that make sense? I have Vx times d by dx, Vy times d by dy, Vz times d by dz. So this whole thing, multicolored, so dv dt plus v dot grad v. This bit here has a lot of very interesting properties that we will talk about, especially when we get to turbulence. This term here makes chaos. It makes small-scale structure. It makes things complicated. It halts our ability to really fully describe the solution space to this equation. It's beautiful and fascinating. All I've written down so far is A, but I took a minute to get there, and I wrote out all the steps, and I spent a second with it. Okay, so this is the acceleration. Now, spend a minute just on A. Let's talk about F. Where's M? Okay, we need an M. We'll put a row right here. Now I have MA. So what's the F? What is the force? So if I have a little parcel of gas, the force that gas experiences is going to be what? It feels pressure. There's pressure all over the surface. So there's pressure everywhere. the net force that it feels is the difference in pressure from this side to this side. So if I have a little tiny volume element of force, the net pressure that I feel is the difference. Or you could think about it as, I'm going to go around and add up the pressure on the surface, and then use divergence theorem. And I'm going to get the total force is grad P. And it's minus grad P because things move away from pressure gradients. And you're done. I got what I got up there, except for that last term. That last term we'll talk about next week. I wanted to talk about these terms this week. So we'll just move the rho over there. Minus 1 over rho, grad P. Now we have Euler's equation, or most of Navier-Stokes' equation. Okay, this whole board right here, internalize that. Consume and make sure that you can do that again, because I'm going to ask you to go through all that again. I want to make sure that you guys can do that, because it's an exercise in taking words and turning them into horrible math equations. So these are my two favorite equations. And am I done? No, almost. How much further down? How much further up the tree do I want to go? I think I'm going to stop there. I got 5 minutes, but I don't think that I'm going to say 5 minutes worth of useful things in the next 5 minutes. Does anybody have any questions about anything I did right now? So the math that I did is intro-y. Most of the class is not going to be that slow. This stuff is crucial, and we'll talk more about it. And yeah.
I just have one really quick question. So the 1 over rho on the right side of the last equation you wrote is from the mass from MA?
Yeah, that's right.
Gotcha.
Yeah, so we wrote down MA, or really rho dv dt. And then I moved it over there just so that I have an equation of velocity. You can also write down an equation for momentum, d rho v, which we'll do later. Because that's really what force equals. Force isn't mass times acceleration, it's the time derivative of momentum. Okay. Let's see.